So we're back. It's getting close to 5 after 5. This has been going for about half an hour. I did turn it up all the way to the maximum spin rate, and I ended up having to turn this up about halfway between 50 and 100 on the hot plate. Keep this at a temperature of about 54, 55 degrees to make sure I kept a good drip rate, maintaining reflux off that condenser. Reaction's quite dark, and if I turn it off briefly, you can see that there don't seem to be a lot more magnesium chunks. So it looks like most of the magnesium has been consumed. When I stir it, I don't see a lot of magnesium chunks floating around. So I think the reaction is pretty much gone. If we really wanted to check, we could kind of lift this up. Take the thermometer out first so it doesn't fall over. Just kind of lift this up and have a look at it. Scoop the sand off there. And you can see that there's pretty much no magnesium left, which is good. Scoop that back down in now. So I'm going to turn the heat off, because when we're adding the 2-methylcyclohexanone, we don't really want the heat. And I'm going to grab, I guess I can grab that with my hands. It's not that hot. I was going to say I was going to grab some tongs, because I'm going to want to remove the sand bath while I'm adding the other material. So I'll just kind of lift that up, scoot that sand bath out of there for now, so we can maintain stirring but not heating. And I'll lower that stir rate back, and we can get a good look, confirm that the magnesium is consumed, which is what we were hoping for. So we'll just let that cool a little bit. And I'm going to grab the graduate cylinder back out so we can add 10 milliliters of ether to our separatory funnel, making sure it's closed. And again, the ether is less dense than is the 2-methylcyclohexanone, so you want to add this first, and then the pressure of the syringe pushing that in there will cause it to mix well. 11 milliliters, close enough. So, unfortunately, that won't stay anhydrous, so we'll have to use it for things that don't require anhydrous ether. And that's stuck. I'm going to pour the ether in. At this point, I don't need this to be dry anymore, so I'll go ahead and leave this out. I can use it for the ammonium chloride. And since I didn't use the 10 milliliter graduate cylinder, I can put that away. I'm going to leave the magnesium in there and transfer that back to my research lab at some point. So now we want to measure out 2.27 milliliters of the 2-methylcyclohexanone and add that in. I'm actually going to use a brand new syringe, just to be safe, since we have plenty. I don't feel like doing this reaction again, because that syringe has alcohol in it. And I'm only almost certain that it doesn't. There's 1 milliliter. And there's another 0.5. And there's another 0.77. So a total of 2.27 milliliters. Make sure all that went in. And we can just let that evaporate back there as well. Put this guy back on. So we got our brown solution. It's still a little warm. Plate's still just a little warm. And now I'm going to be adding that dropwise. Just let it cool just a little longer. And we want to add it again at about 1 drop per second. And that's also a pretty exothermic reaction, so the reflux may continue by itself. So we can start adding that. Drip, 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 drip. Yeah, it seems like that's about 1 drop per second. And that brown solution will probably change color again. As we add this. Product is a colorless liquid. Won't be a colorless liquid when we're finished with this reaction. Probably it'll be a little bit orangey, but after purification hopefully it'll be colorless. And we'll be purifying it by column chromatography. It's a good way to separate a relatively non-polar ketone with just a dipole-dipole interaction from the alcohol that has hydrogen bonding. We can put the 2-methylcyclohexanone away. Done with that. And it's about 10 after 5. We'll kind of see how long it takes. About 12 milliliters at 1 drop per second and 20 drops per milliliter. It's about a milliliter every 20 seconds. So while I'm waiting, might as well measure out my 10 milliliters of saturated ammonium chloride that I'm going to use to quench this reaction. And it can just sit there until I'm ready. Put this guy back. It's gotten a little bit less dark, kind of a tan color now. we are still refluxing. You can see that the solvent is dropping off the condenser, which means that just the heat of this reaction is enough to keep that boiling without any external sand bath. And we're still dripping at 1 drop per second. And I think you can see that it's a little cloudy because of the reaction boiling again. We want to make sure that this is added slowly, because another side reaction that can occur if the ketone encounters base, and the phenyl magnesium bromide is a base, is it can actually take one of these protons off to form what's called an enolate ion. And that enolate ion can react with another molecule of ketone in a reaction called the aldol condensation. And it could happen on either side. And that will form a new carbon-carbon bond. And upon protonation, it would generate an alcohol. That one won't be particularly stable, but if the enolate formed on this side, and then that reacted with the ketone, then that product is stable. And I'm going to flip it around so I can draw it this other direction. And I've protonated it. Because there's an additional hydrogen here next to the carbonyl group, which could be removed by base. To form an enolate again. And this is a reaction you're going to learn about. Which can then come back in and eliminate the alcohol, and the product you get is actually an alpha-beta unsaturated carbonyl compound by the aldol condensation, and we don't want that compound. So we want to make sure that the carbonyl compound is going to run into phenyl magnesium bromide and react at the carbonyl, and not get deprotonated to form this enolate and undo this, and go on this aldol condensation. The aldol condensation product is a different molecular weight. We may see some of it in the GC mass spec analysis of our product, along with that biphenyl. So that's why both the order of addition and the rate of addition is actually relatively critical to avoid unwanted side reactions. The Grignard reaction is not a high-yielding reaction in most cases. So we're still dripping nicely, slowing itself down again like it did before, so I'm going to increase that rate a little bit. We've still got some reflux, but notice it stopped dripping as the rate slowed down. This is a typical behavior of these condensers to gradually stop themselves. These septphonals, rather, these stopcocks. And I have to judge a little bit because I've got some reflux going on that's causing it to drip as well as the rate of addition. So we just kind of mess with that. I'm going to keep this rate of reflux reasonably constant. So basically what I'm trying to do is equalize the rate of dripping so that it's pretty close to the same rate off the condenser and off the separatory funnel. And it's kind of a judgment call. You see that there's some salt, right? That's where it's dripping down. It's actually dripping down the wall. That's some magnesium salt, and the solid that you're seeing here is also some magnesium salts. That's fairly typical of the Grignard reaction. A lot of that will dissolve in the ammonium chloride. So I got a kind of a cloudy, slightly tan solution now. A little bit of solid on the walls, just where it's dripping down. You see that it's not really dripping off the tip. It's actually dripping and kind of hitting the wall of the Claisen adapter and then dripping down the side of the flask, which is why we see that solid over there. I slowed it down a little bit, and it slowed down the rate of dripping off the condenser as well.